Okay, we're going to start talking about the last section in this stereochemistry thing, and that's chiral molecules. We're going to go back and forth over this, and I'm going to ask you to shut the video off at certain times for you to do things, okay? Because you're going to build some models. And do it. I know I'm not there to observe you, but make sure that you do these things. Anyway, I kind of start with a fun thing. That in the lab, there should be some packages. I know I left them on top of the tennis ball models on the right-hand side of the classroom in the corner. You'll find a bunch of plastic bags, and in it you'll find some nuts and bolts, and you'll find some pasta, and you'll find some clear plastic, which I'll talk about in a few minutes. I'd like you to take these two items, okay, and compare them. How are they similar, and how are they different? Turn the camera off or turn the video off and examine those things and fill in the bottom of page 317. And I'll be back in a few minutes. Don't skip this step. It's kind of fun. Okay, we're going to start with the nut and bolt, and hopefully there's lots of little differences in them. And lots of similarities as well, but the major thing that you should have noticed if you try to turn the nut in the bolt, you'll notice that if you turn it in a counterclockwise one way, if you try that with the other one in a counterclockwise, one sends it this way, one sends the nut the other way, and this is actually called a left-handed thread. And it has handedness to it. Very hard to find. Took me a while to a lot of phoning around and stuff like that. It does have a special application to it, especially for motors that have wheels that are turning at high speed, and if you don't want them to become unstuck to whatever they're stuck to. And this one's a little harder to see. If you look at the pasta, again, it was very hard to find pasta. But if you look at them very carefully, they're actually been turned in opposite directions. So somewhere out there's a pasta maker that's just turning things in a different direction. I don't even remember what's most common, but I got a lot of raised eyebrows when I went into just about every grocery store in Ottawa trying to find pasta that was turned in a different direction. So we would say that these things have handedness, just like our hands have handedness. And that's what we're going to study in terms of molecules. There's lots of examples of this if we turn to page 318. And if I was in class, I might give you some of these, but we have limonene, have examples of handedness. Okay, so left-handed limonene is found in lemons and right-handed in oranges. Carvone is the one I usually demonstrate in class. I give you some spearmint gum. Sorry, I'm not there. Our carvone is found in caraway. I've actually got some in that container that had all your samples on them. And we don't eat a lot of caraway, but they taste different. Here are some other ones, and we're going to come back to these molecules. Ibuprofen has handedness. Thalidomide, and thalidomide has a very negative history. It was a property given to women in their early stages of pregnancy to prevent nausea, and then they found out it gave horrible birth defects, and it had to be stopped. But they basically found out what was going on. I think it was the Germans that were able to send out an alert on there. Anyway, and then the next thing is dextromethorphan. So we're going to come back to those molecules in a bit just to show how you figure out whether they've got handedness or not. So the next thing I'd like you to do is to in your small groups is to get together and get out the molecule making kits. And I'd like you to make the following molecules, okay? Actually, I would like you to make 4. So I'd like you to make a molecule with all the same color on the outside, so the carbon in the middle, the black, and then 4 the same molecules. I'd like you to make one. This is the CH3X, so carbon in the middle with 3 yellow and 1 other color. It can be green. I want you to make 2 of each, is really what I mean. So I've got 2 of these, if you notice. And I've got 2 of these. Okay. And then I'd like you to make a CH2XY, so 2 yellows and 2 different colors. Okay, and if you'd make those, and then the last one, you want to have a central carbon and 4 different colors on the outside. Okay, and you want to make those up so that they're mirror images of each other. Okay, and okay, so what we'd like to do now is, first of all, I want to just discuss mirror images. So I'm going to take away the paper, and I'm going to stand up. So if I look at this molecule and I place it down on a mirror, you see I've got a mirror here, and I'm just going to tilt the camera a little bit. You can see the mirror image in the mirror. You can also see me. Hi. But you can see the molecule, and you can see that what's sticking out from the mirror sticks into the mirror, and that's what we would say is its mirror image. So its mirror image of this molecule looks like this. Okay, so there's the mirror image. And what you want to do with all the different molecules that you have is to take the mirror image, the model of your mirror image, and take it out, and can you align them correctly? Okay, so that's what I'd like you to do. So make the 4 sets of molecules, okay, and put them in a mirror image situation. Okay, so you can do that in a number of different ways. There's 2 molecules in a mirror image. Okay, if I look at this, and again just tilt the camera, you can see the mirror image. Okay, and then take them out from the mirror and see if you can align the molecules. So I'll give you a few minutes to do that. If you just make up your molecules and then come back to this. Okay, well, hopefully you've done that, and now let's go. We've done the first molecules, but if we look at this one, there's my molecule with one CH3. I don't know, it could be a chlorine or something like that. And if we tilt that, we see that the mirror image has the green pointing away, so it looks something like that. And if I take the mirror image molecule out, you can see quite plainly that I can align those very, very easily. Okay. Similarly, if I take these molecules, so now I have 2 different groups. I don't know how you align them, but if that's on my mirror, and again I tilt my camera, you can see that the green is going farthest in, and then the other ones all line up. So green farthest in, and there are the mirror images. Okay, mirror image model. So, sorry, they're a little bit out of focus because I'm focusing on the paper. But if I take that molecule out, I can align all the different colors. Okay, so that's that molecule. And then the last pairing, now this one's a little bit tricky, but I've got the purple pointing upwards. Let's put it that way. Again, I'll just tilt my camera a little bit so you can see that orange against orange, yellow against yellow, green against green, and the purple pointing inwards. Okay, so if I mimic that here, so orange against orange, yellow against yellow, green against green, and the purples lined up opposite to each other, if I now take this molecule around, okay, there is no way that I can align them so that all the colors match exactly. It's like, oh, okay, well, I gotta, oh no, well, that doesn't work because I gotta now. So there's no way that you can do that, and you should verify with your own models that that is true. So again, just turn off the video for a few minutes and just verify that you have those kinds of situations happening with all of your samples. Okay, so now we're back to the notes. I'm going to go back to page 319, and this is where we sort of define our stereochemistry, or what it's concerned with the three-dimensional nature. And we want to talk about this specific situation here where we have 4 different things attached to a central carbon atom. And we're only going to talk carbon in this course. We could talk nitrogen and a number of different things, but we're just going to talk carbon. And with this kind of thing, you can't, we call these enantiomers. Okay, so that's defined in the second paragraph. That's an enantiomer. It's a molecule having non-superimposable mirror images. Okay, so if I There are their mirror images. Okay, they're non-superimposable, and it usually results when you have a tetrahedral carbon atom with 4 different things attached. Okay, so we have to have 4 different things attached to them. And if we look at the diagram in the notes, there's a molecule. If we look at this molecule here, we've got an acid group here, we've got an OH, we've got a hydrogen, we've got a methyl group. And so those are the 4 different things. So this would be called an enantiomer, and there would be 2 of them. And you would designate this is called a chiral carbon. Chiral, C-H-I-R-A-L, and you designate it by using a little asterisk by the carbon. In case you're ever asked on your exam to show where the chiral carbons are, you can just use a little asterisk. So now I'm going to ask you again to go back and to go back over the molecules that we were looking at before. And where's my first page? Go back to page 318. And in some of those molecules that you were looking at, see if you can find the chiral carbons. So you would have to go through each one, and here you can see there's 2 different groups, so they're not chiral. And here there's 3 hydrogens attached. It's not chiral. This doesn't even form 4 bonds, so it's not chiral. But if we look at here, we've got a group here, a group here. Now you might think, well, this is just a chain, a ring, and remember there'd be a hydrogen attached somewhere. But if we go around the ring, you can see it's not symmetrical because of this double bond. And so going this way and going this way would be considered different molecules. So that's where you would find your chiral carbon. And there I've marked it with an asterisk. Okay. So do the same with limonene and carvone, ibuprofen, thalidomide, and the dextromethorphan's on the next page. Okay, and I'll come back after a few minutes. If you come back after a few minutes, shut down the video, and then we'll go over that. Okay. Okay, we're back, and hopefully you found the chiral carbon. This one's very similar to the one we just did. There's your chiral carbon right there. How about for your ibuprofen? Did you find a chiral carbon there? This is a little trickier to find because we haven't written in anything. Remember, here would just be 2 hydrogens, so that's not chiral. Okay, and then we've got, we don't have 4 bonds there. But if we look here, we've got a hydrogen, we've got a methyl group, we've got a group with a benzene ring and a whole bunch of other stuff, and then we've got here a carboxylic acid group. So there's your chiral carbon in ibuprofen. So ibuprofen, only one of the enantiomers will probably work. And if we go with thalidomide here, we can also see that we have a similar situation. Here's a carbon here that is going to have, it's got a hydrogen, a nitrogen, and a whole bunch of rings, another nitrogen group here. And if we go around the ring, there are differences between them. So that would be a chiral carbon there. And we're just going to deal with carbons right now. We're not going to deal with nitrogens, because I think some of those nitrogens might be chiral as well. Okay, so that's how you would pick out, and be prepared to pick out those on your exam, because they might come up from time to time. So now we're going to come back to page 320, and we're going to say, well, what's meant if we said something's optically active? This is very cool stuff as well. So ordinary light, when it passes through the atmosphere and stuff like that, oscillates in an infinite number of planes. Okay, and at right angle to that, you've got these waves traveling right angles to the direction that the light is going, and that's called a transverse wave if you've taken some physics. Now, when it passes through a polarizer, only light passing in one plane gets through, and that's called plane polarized light. What I've done in your kit is that you should have gotten 2 pieces of sort of darkened plastic, and this is polarizing. These are polarizing filters. Okay, and if you take the filters and you put the 2 pieces together and look through a light and you rotate those things around, you're going to notice really cool things happen. I just better make sure, yeah, it's happening on the camera as well. So you'll notice that things are happening here. Okay, and let's see, do I have a I'll show you something else that's pretty cool too. If I start up my iPad, okay, so there's my iPad. Can you see the symbols on there? Oh, you can see my reflection certainly. But if I take that and I rotate it around, if you notice the symbol, you can see a symbol. Okay, I've got some weird light going on there. But it sort of disappears after a while. So you can do that with your computer screen because it's giving out plain polarized light. You only need the one. And I didn't get it out, but it would take a while. But photographers use polarizing filters to cut down on the light. So those are known as polarizing filters. It's very cool stuff. It was developed by Edwin Land of the Polaroid Land camera. And we can use this. We can make something that we're going to call a polarimeter if we put polarizing filters on either end of a tube, and we can put optically active material in there. Because this stuff, when we talk about enantiomers, they're optically active. They are going to rotate plain polarized light in one direction. One isomer, one enantiomer is going to rotate it in one direction. The other is going to rotate it in an opposite direction. And I've tried to outline this. I know the graphics are a little bit cheesy on this, but here's my light here, and here are my rays, and I've just indicated different planes that the light is passing through with these arrows. And if we put up a polarizer, so there's my polarizer, light only going in the up and down direction is going to get through. So that's called plain polarized light. You should know that term. Okay. Anyway, they noticed that if we do this in a slightly more complex graphic, if we have the light, we've got our light traveling all directions, we put it through a polarizer, okay, and then the light goes through these enantiomers, so that's indicated here. It's going to rotate the light, and so what I would have to do to see how much it's rotated the light is I would take another polarizer and I would be able to rotate it to see when the light would come out. So I would be rotating this in order to maximize the amount of light that is passing through the whole solution. And that number of degrees will tell me something about the molecule that I'm dealing with. And if I have one enantiomer, one pure enantiomer in there, I'm going to rotate it in one direction. If I have the other pure enantiomer in there, I would rotate it in the other direction, and assuming they're the same concentration and everything, it would be the same number of degrees, just in the opposite direction. Okay, and that instrument is called a polarimeter. We have one in the lab if you're interested, and Zhao Zimmerman a couple of years ago did an extended essay, and he used the polarimeter to study enantiomers, so pairs of enantiomers, and he got a very good mark on it, I might add. Okay, so if you can just read through that, and we would say, well, if something's rotated clockwise, that's dextrorotary, and counterclockwise would be levorotatory, and different molecules will have different abilities to rotate light. So in terms of enantiomers, they would have exactly the same physical and chemical properties. You might wonder, why do they taste different? Well, obviously because the molecule is in a slightly different geometry, that it would link up with your taste buds a little bit differently, and so they're going to taste different. Only one enantiomer, usually of any kind of a drug or a medicine, will have its therapeutic effect, and the other ones may not, because the shape is very important. But so same chemical properties, slightly different chemical properties that way, but generally speaking, all the other ones, they would react to acids and bases and oxidation and reduction all the same way, and they would have all the same physical properties as well, except that they rotate plain polarized light in opposite directions. Okay, so optical isomers, as I put down here on the bottom, page 321, identical physical properties, they just rotate light differently. If you have both in the same mixture, that's called a racemic mixture, and or racemates and that kind of thing. That's how that works. The IB, just to throw this on, the IB wants you to know about diastereomers as well. They are mirror images of each other that are non-superimposable, but they're non-superimposable because they have two stereo centers, and their configuration of one of them is a little bit different. And I think if you just flip the page, I've given a couple of examples there of what diastereomers are. There's also a couple of examples in your textbook if you have any trouble. Those are sort of three-dimensional drawings, so I think the one in your book are pretty good. Okay, so you can have enantiomers and you can have diastereomers, but diastereomers you definitely have to have different two different stereo centers. Okay, that's all for now. There's some homework there at the bottom of the page, and this stuff can be really tricky. That's why I said having the models I think is really useful, and I'll answer any of your questions when I get back to class. Okay, thanks, and I'll see you tomorrow.